So, welcome to the second day of the Gravity Wave School. As you really learned yesterday, what is it that we are going to learn today? And if you had a preview of today's lecture, you would see that there's a lot of exciting things which are supposed to happen in today's lecture. So with that, let me invite Bernhard to continue with this course. Bernhard, all yours.
Yes, thank you very much. So a few comments on the plan for the next lectures. Because we couldn't finish the part of massive stars in their nuclear synthesis, I will actually defer the nuclear synthesis to the fourth lecture, and that'll be taken up. It just fits together well with the nuclear synthesis from supernovae. So the topic today is what is happening to the iron cores of massive stars in this region between about 8 and 100 solar masses for single stars once you finish silicon burning. That's really, well, I'm biased if I'm saying that, that's really the interesting and exciting parts. Lots of things happening within a few seconds or hours until you see the whole explosion at the surface. Okay, there are a few more reviews that I can suggest to you on this topic. As further reference, they are all pitched slightly differently. There's a lot of elements coming together, from the physics of core collapse and explosion to its numerical treatment, both the treatment of the fluid dynamics and the transport, the radiation transport processes. These are really two topics of their own, which are more covered in these last two reviews here. Okay, and I'm also going to give you a bit of background, a slight bit of background in the first few slides about what we know observationally about core collapse supernova explosions. I don't know how much time I will actually be able to devote to this on Friday. So it's, I think, advisable to not skip these aspects completely. If you're registered for the school, you're all aware what core collapse supernovae are in principle, explosions of massive stars, and you've seen the pictures of them, supernovae outshining an entire galaxy and the beautiful remnants that they make afterwards over the next decades, hundreds, thousands of years. And of course, they were first observed historically before we knew what they are. There are several historical records of stars that appear and disappear, sometimes termed guest stars, as this famous one from 1054, observed by Chinese astronomers. We now know that this was an explosion, a very bright explosion, visible by the naked eye, at the spot where we see today the Crab Nebula with a pulsar in the middle, but it was only in about the 1930s that this connection was fully made, and Edwin Hubble appreciated that the Crab Nebula is actually the remnant of this event observed in medieval China. So this is maybe a bit biased because it's very much from a European perspective. If you dig into early supernova research, it's really a very multicultural thing. I mentioned the Chinese observations. I'm sure there are Indian observations. I know there are indigenous Australian observations of supernovae. So this is a bit biased, but I think all cultures have in common that they are fascinated by stellar phenomena. And in Europe, these observations of new stars, they were called novae at the time, indiscriminately by Tycho and Kepler, were very important in Europe in changing the notion of immutable skies at the further celestial hemispheres. Observations in our more nearby galactic neighborhood are actually not so frequent. There was one there was a new star observed in the Andromeda galaxy in 1885, which at the time was also just called a nova. We now know that this was a supernova based on the observational data, the observational records. This is incidentally a star that featured very prominently, well, not very prominent, but at least it did feature in James Joyce's novel Ulysses. And it was only in the late 1920s and in the 1930s that people began to picture together what actually happens physically in these novae, or now a subclass of those of interest to us were then called supernovae. So after Hubble made this link between the Crab Nebula and the guest star of 1054, very shortly afterwards, the neutron was discovered, and physicists immediately, or almost immediately, put together this notion that neutron stars composed of neutrons might exist as the end stages of stellar evolution. And in the mid-1930s, Bada and Zwicky then realized that among what people had called novae so far, there was a distinct subclass of much brighter stellar transients. They call these supernovae, and they posited that one class of supernovae, the ones that we now call core collapse supernovae, are powered by the collapse of a massive star to a neutron star, because they argued that the gravitational energy released in that collapse would about explain the energy budget that they inferred from the light curves and spectra of these supernovae. Neutron stars, the discovery of neutron stars then had to wait a little further. And in the late 1960s, this association of the Crab with supernova 1054 was tied down further with the discovery of the Crab pulsar. So we really knew then that there was a neutron star at the place where there was a bright explosion. In supernova in 1987A, when we observed an explosion of a blue supergiant in the Large Magellanic Cloud, this was, well, definite observational confirmation of what we had, of course, long theorized, that these one type of supernovae, these core collapse supernovae, are indeed explosions of massive stars. Supernova 1987A was the first event where this was actually observed, massive star exploding and then disappearing and leaving behind a remnant. We now also have found a neutron star for that explosion. Yes, confirmed the theoretical picture that we had long had, and the detection of neutrinos from that explosion also confirmed really that there was a huge release of gravitational energy, from gravitational collapse involved. Now, before we go into the theory of these explosions, we should get a few boundary conditions. It's always advisable in theoretical astrophysics to get have a few boundary conditions, rough numbers of the masses and energies that certain phenomena actually involve. And if you look at the supernova types that we know, so the one that classifies supernovae, there's actually one subclass, the 1As, which physically turn out to be something different. And observationally, they form, these thermonuclear explosions form a subclass of the so-called type 1 supernovae, the 1As. So observationally, you can't really tell what the mechanism is. You only see a surface phenomenon. But in the end, the distinction of different explosion channels fits with the spectral classifications. So supernovae are classified spectrally, first according to whether they have hydrogen in their spectra or not. Those with hydrogen are type 2s. The others without hydrogen are type 1s. And among the type 1s, you have, which apparently must have lost, so either they must be stars, come from stars that have, that are not evolved massive stars at all, or they might be massive stars that have actually lost their hydrogen envelope. You have there the type 1As, which have silicon lines, strong silicon lines. These form a class of their own. Among the others that don't have silicon lines, the 1Bs and 1Cs, you have those that show evidence of helium in their spectra, called 1Bs, and no evidence of helium in their spectra, these are called 1Cs. The nature of these, aside from the fact that they have lost their hydrogen envelope, whether they come from stars that have undergone extensive wind mass loss, or whether they have lost their hydrogen envelope by binary interaction, that is something that needs a little more thought. I will come to this in the last lecture, but suffice it to say that we believe that the majority of these, as I already hinted to yesterday, actually do come from stripped binary stars. And among the supernovae of type 2, which have very prominent hydrogen lines, there are still a few subdivisions that relate on the one hand to the amount of hydrogen that's left. So a subclass called 2b has actually hydrogen lines that disappear later during the transient. And then you have further distinctions based on the shape of their light curves, whether they have a plateau, a long plateau of roughly constant luminosity or not, and a few other minor distinctions might also creep in, which again can wait for the last lecture. The importance of the light curves and spectra is that they allow us, and I won't go into very much detail there, they allow us to infer rough properties of the energies involved in these explosions, kinetic energies, the masses, and to some extent, to a large extent, also the power source that drives the light curve. The power source that drives the light curves is a little different depending on the type. So the type 2s are mainly driven by the thermal energy of the explosion, the shock heating, the thermal energy of the red supergiant envelope that has been heated by the shock. The other types are primarily powered by the release, or their light curves are powered by the release of energy from radioactive decay, in particular of 56 nickel and to its daughter nuclei. In the so-called type 2p supernovae, those will only power the late time tail of the light curve. That can still be used to estimate how much nickel is there. For the type 1s, the decay of nickel is at least very probably the primary source of power for the light curve. So you emit from the nickel 56 decay and the decay of its daughter nuclei, gamma rays as well as positrons. Those thermalize and eventually the energy gets converted into visible light. Yeah, so this is important because it gives us, as it allows us with the help of radiation transport theory, estimate ballpark numbers for a few important quantities. So explosion energies, the kinetic energies of these events range over, well, at least 2 orders of magnitude. The average typical number is about 10 to the 51 ergs. Ejector masses can vary quite a bit. They can get up to, well, of the order of 20 solar masses. And you produce, again, let's say on average, a few hundredths of a solar mass of radioactive nickel 56, again with a widespread. All right. Yeah. So this already puts some constraints on what the mechanism might be. Yeah. Basically, these ballpark numbers, energies of about 10 to the 51 ergs, leave us with two possible sources of energy to power the explosion. Yeah. So on the one hand, you could generate that much energy from the collapse of a star or stellar core to a neutron star. The energy that you release this way is of the order of the binding energy of the neutron star. That's actually much more than 10 to the 51 ergs. That's of the order of several 10 to the 53 ergs. So if that's the case, you are actually facing the question why so little of that energy ends up in the kinetic energy of the explosion. Yeah. Why that is the case is this is something that we'll understand very quickly. The other possible source of energy that conceivably can generate 10 to the 51 ergs is nuclear burning. And it's, of course, very hard to burn something, a large amount of, let's say, hydrogen directly to the ion group. That would require very extreme conditions. So scenarios that might be more, that are realistic, would rather involve burning from, let's say, intermediate mass elements like C and O in a carbon-oxygen white dwarfs to the ion group. You need to burn about 1 to 2 solar masses of carbon and oxygen to ion to get into this to this ballpark number of 10 to the 51 ergs. So in the explosions of type 2 and type 1b and c, we don't really see that much radioactive ion group material. That rules this out as a power source for the core collapse supernova explosions as massive stars. Yeah, but this is what primarily powers thermonuclear supernovae. Yeah, for thermonuclear supernovae, you burn about 1 solar masses of that carbon oxygen material to ion. That might be from a single white dwarf, or it might be from colliding white dwarfs, doesn't matter, doesn't change the order of magnitude. And similarly, these pair instability supernovae that I've hinted at would also be thermonuclear powered. So in that case, you'd be talking about burning tens of solar masses of oxygen to the ion group that will then give you very powerful explosions in very massive stars. Yeah, but in the normal massive stars, this, based on hindsight observational knowledge, nuclear burning can't be the power source. Yeah, you don't see enough ion group material around for this to work. Okay. But the good thing is about the core collapse supernovae, the core collapse supernova scenario, is that, as I hinted at, alluding to supernova 1987A, that we actually know that the scenario of a massive star collapsing to a remnant, or at least making a big explosion, that this happens in nature. This is somewhat different than for the thermonuclear explosions, where we don't actually know for sure what the progenitor systems are. By now, we have identifications of progenitors for exploding massive stars. These come from archival images of galaxies where stars could be, where progenitor stars could be identified, and then they were associated with the location of a supernova explosion. And as you continue to look at the location of the supernova, you now see, well, this supernova, as it's stimming, is really sitting at the location where this massive star was. So you get a direct identification of some progenitor systems. This can be done for still only relatively nearby supernova explosions. And especially for the type 2 supernova explosions, we have identified that these come from red supergiants. There are several identifications, and the observations suggest that based on the brightness of these progenitors, which we can match to evolutionary tracks in the HR diagram, these probably come from a mass range of about 8 to 18 solar masses of the progenitors on the main sequence. Yeah. For supernovae with a stripped envelope, the 1Bs and the 1Cs, and also the type 2Bs, which are sort of stripped, so they have less hydrogen around than they should have. Identifications are much more scarce, and their nature is still a lot less clear. But based on statistical arguments, I already said yesterday that we are pretty sure that the majority of 1BC supernovae probably have undergone stripping in binary systems. Now, this might be a good place to stop for a minute for questions that have come up so far. Let's look in the chat.
Yeah, can I ask a question?
Yes, sure you can.
My question was, so you said that type 2 supernovae have hydrogen in their spectrum.
Mm-hmm.
But I mean, I'm a bit confused because the hydrogen burning state is over, right? By the time.
Yes, but we'll get, maybe I just jump ahead to the next slide because that explains it. So bear in mind that the nuclear burning always just occurs in the core, that most advanced burning stage, and you'll finish. So after hydrogen burning in the core, you still have about 90–80% of the star left unprocessed. Yeah. So hydrogen burning in the core will only consume part of the hydrogen in the star, only in the inner regions. Yeah. Now, the various shell burnings, so shell burning of hydrogen will imply that regions further outside will also be burnt during the subsequent evolution, but you always leave much of the material in the envelope just unburned. Yeah. This is the region where the star never gets hot enough to actually do any nuclear burning. Yeah, does that answer it?
Yes. So I just had one more question. So, yeah. So you mentioned about stripped stars and binaries.
Mm-hmm.
Stripped, by stripped, you just mean that the outer layer is not present. What does it actually mean?
Yes, it means that the hydrogen envelope has been removed. Yes.
And this happens due to some tidal interactions?
Yes, due to Roche-lobe overflow, yes, things like that. Yes.
Okay, thank you.
In principle, it can also happen by winds, but for these, we believe that in the majority of the cases, mass transfer in binaries is responsible. And in principle, the mass transfer in binaries in some scenarios can go a bit further and actually strip some helium as well, but that's probably a more rare occasion. It requires certain system parameters to be tuned such that you can even strip some of the helium. Yeah. Okay, more questions?
Excuse me. Could you go back 2 slides?
Yes, this one here.
Sorry, the next one.
Previous one?
Yeah, in this diagram, the light lines, I noticed that the relative flux for different types are higher than one another. So is there a difference, or is this just an error in the diagram?
You mean this thing here in the diagram, this relative flux? these are really just offset with respect to each other. Yeah.
It's just an offset.
So this should not be confused with one B's being brighter than one C's or so, and brighter than type 2s. In generally, the type 1As are the brightest ones. Yeah. And some type 1Cs are very bright because of high explosion energy. But for most of their evolution, the type 2s are actually somewhat brighter than these 1Bs and 1Cs on this luminosity plateau that typically lasts for about 100 days. So don't take this as a hierarchy of one type being brighter than the other. That's true mostly for the type 1As, but among the core collapses, it's a bit different. Yeah, further questions?
Hi, Bernhard.
Yeah, someone asked, how do we classify hypervelocity stars? Oh, that's a very different question, actually. Because hypervelocity stars, well, they're characterized by the motion with respect to, let's say, the average velocity distribution of stars in the galactic disk. Yeah, you can classify these differently. And some of these may be associated actually with some sorts of stellar explosions. That's actually not really so much my field, but so the hypervelocity star classification refers to the motion relative to the overall galactic rotation. Yeah, that doesn't have too much to do with explosions by themselves.
Hi, Bernhard.
Yes, yeah.
I have a question from your next slide.
Yes.
The next one. Yeah, thanks. So you said that the gravitational binding energy of neutron stars must be like order of magnitude higher than the energy budget of the ejecta, and why should that be? Like, why is not the binding energy just transferred into the kinetic energy of
yes. The answer will be, we'll come to that shortly, but the answer will be that most of that energy is released as neutrinos, and most of these neutrinos never interact with the matter. Only a small part does, and that's what actually powers the explosion in most cases. Yeah, it comes down to the fact that most of the stuff goes out in neutrino radiation without ever interacting with matter again. That's what brings this down by 2 orders of magnitude.
Yeah, thanks a lot.
Mm-hmm. Do we have more questions? So then I think we can continue. So yeah, as what we basically covered last time is that a massive star will evolve this characteristic onion shell structure with various shells and an iron core at the center. And when you have an iron core, of course, that iron core can't undergo any more exothermal fusion reactions. Yeah. So the iron core will, and around the iron core, you may still get periods of shell burning, silicon shell burning at its edge, which is going to add mass to the iron core. Yeah. And once the iron core becomes massive enough, something will happen, and that will then go into this sequence of phases from, let's say, the initial collapse of the iron core down to the formation of a neutron star and the launching of a shock wave, which then stalls and then is finally revived, and then you get an explosion in the end. And that's what's going to be the subject of the next part of this lecture. So if we have an iron core in a massive star, and there's no nuclear burning, it will be cooled by neutrino emission. It will evolve to relatively low entropy. And under these conditions, as we discussed yesterday, the power, the source of the pressure is primarily the degeneracy pressure of the electrons. Yeah, that degeneracy pressure goes with rho times the number of electrons per baryon to the power of 4/3 plus a few finite temperature corrections. A very important quantity here is this ratio of electron to baryon number. This is called the electron fraction YE. We'll encounter this quite a few times. Now, if you solve the stellar structure equations, you find that you get a limit for how big such a degeneracy supported configuration can be. It's actually a little more complicated if this degenerate object doesn't sit in vacuum but has some other shells on top of it. But roughly the stability limit, the famous Chandrasekhar limit, is still a good means to assess the boundary conditions for the stability of such degenerate ion cores. And the upshot is, so it's really the number of electrons per baryon that enters here. The electrons provide the pressure, the baryons contain most of the mass and are responsible for the gravity. So you get a limiting mass. You can show that by solving the stellar structure equations, which scales with electron fraction squared. Yeah. And for sufficiently high, so supposing you had symmetric matter, that would put you with the same number of neutrons and protons in the nuclei, that would put you to about 1.4 something solar masses. But at very high density, something else comes into play, and this is really what is responsible for the collapse. At very high densities, the electrons have a huge, still, even if at zero temperature, have quite significant internal energy, yeah, because the Pauli principle says they must live at quite large momentum and quite large energy. So it becomes favorable for them to be captured on protons and either protons within nuclei to form a more neutron-rich nucleus, or free protons. Even if you have rather, in terms of degeneracy pressure, rather cold matter, it's still several gigakelvins. You'll have a few protons around, and captures on those can also be important. In the process, you eat an electron and you emit an electron neutrino. Yeah, and the electron neutrino, unlike the electron, isn't trapped in the matter, yeah, because it's not electromagnetically charged. So the electron neutrino at this stage can just escape freely, and you're left with less electrons per baryon. Yeah. As a result of that, your Chandrasekhar limit will go down, your degeneracy pressure will go down, and the star actually has to contract further, and that accelerates this whole process of electron captures. If you're looking at the more massive stars, then there's also another effect that comes into play. In the more massive stars, the finite temperature corrections play a major role. However, the finite temperature corrections come, among other things, from the radiation pressure provided by photons. And once your temperatures get high enough, it will become favorable, however, for those photons to disintegrate ion group nuclei. That reduces the radiation pressure and these finite temperature corrections here, and also does accelerate further contraction. And in the end, the acceleration of the contraction due to electron captures and to dissociation becomes so rapid, happens on dynamical timescales, and then you get into collapse on a free-fall timescale of the core. It's instructive to calculate the free-fall timescale of such an ion core. It just happens to be fractions of a second now. Yeah, the evolution becomes very fast. Okay. All right, so how does that collapse continue? Well, actually, this reduction of electron number, we call that de-electronization, accelerates because the capture rates become faster with higher density. Yeah, they actually go with a higher power than the degeneracy pressure. They go with rho to the ye to the 5/3, so they just accelerate actually. Yeah, and the core becomes increasingly neutron rich, and it becomes neutron rich on slow and faster timescales. However, at some point that will stop. Yeah, when will that stop? So the key thing for de-electronization is that the neutrinos could initially escape freely from the matter. Yeah. However, if your density becomes high enough, then eventually, despite the weak interactions that neutrinos are only subject to, the neutrino cross sections become high enough for neutrino scattering to be important. The dominant source of opacity for scattering in this early phase is coherent scattering on nuclei. So basically, the scattering is relatively efficient, relatively high opacity, because the neutrinos, as it were, see the neutrons and protons as a coherent superposition and not as individual particles. And that implies that the scattering opacity per unit, per nucleus goes like the average mass number squared, and the scattering opacity per unit mass increases with density times the average mass number. Yeah. On the other hand, you can estimate how does the diffusion time scale actually for neutrinos scale with that opacity. How does that scale on with density? Yeah. We'll actually work that out in the tutorials as well. So you can compare the diffusion time scale, which is basically the light crossing time times the number of scatterings over that wavelength. So times what we know as the optical depth. That's distance divided by the mean free path. You can then estimate when this diffusion timescale becomes longer than the collapse timescale. Yeah, and you'll find that at densities of a few 10 to the 11 grams per cubic centimeters, the neutrinos that are generated by electron captures cannot escape anymore. This won't immediately stop the electron captures, but very soon. That's because the neutrinos, as soon as they are trapped in the matter, will equilibrate with the electrons, protons, and neutrons. Yeah, and you may still shuffle a few electrons into neutrons, but you'll get into an equilibrium very soon, and the total number of leptons per nucleon will be conserved. Yeah. The final electron fraction that you reach is a little below 0.3 in that process. You'll get no further lepton number out at higher densities, at least for a while. Yeah. So at that point, the collapse becomes adiabatic, but the star is already collapsing, it's still unstable, and continues to collapse further. The important thing, or one very important thing, however, is that because the electron fraction has been reduced up to that point quite a bit, there's really an inner core that's collapsing the fastest, that is somewhat decoupled from the outer core, which is collapsing at well, in absolute terms, slower velocities, but in relative terms to the sound speed at supersonic velocities. Yeah, so the object that's going to become dynamically important is really a small part of the iron core, the so-called homologous inner core of about half a solar mass. Now, what happens to that core? Well, it still continues to collapse. When does that collapse stop? Well, it collapses only once you get to beyond nuclear densities. So up to nuclear densities and around nuclear densities, the nuclear forces are attractive, but nuclear matter is almost incompressible or highly incompressible. So if you overshoot nuclear density, you'll feel the repulsive interactions. We say that the equation of state becomes very stiff at that point. Yeah, so pressure increases very rapidly with density. And that will, at that point, stop the collapse and of this inner core. And the inner core will not only stop gently, it will rebound, it will spring back like an elastic rubber ball that you try to compress. Yeah, and what you have, though, is that the outer regions of the core, they still know nothing about what happened in this inner core because they're falling in supersonically. They will still be falling in. So you have the rebounding inner core crashing into the infalling shells. That means that everything that's falling in here must be accelerated abruptly in a shock wave. Yeah. So you get a shock wave that's launched at the edge of this inner core and propagates out with an initial energy that's relatively small, only 10 to the 51 ergs, that corresponds roughly to the binding energy of this inner iron core. Yeah, and that's relatively small because this only contains small mass, and this inner core remnant is actually not so compact yet as the final neutron star will be. Give me a second to recharge my fluids. Questions up to that point? Yeah. So back in the early days of supernova theory, when people realized that this rebound of the inner core will launch a shock wave with a kinetic energy of 10 to the 51 ergs, they thought that might be what powers the explosion of the star, because this is exactly the energy that you seem to observe for supernova explosions. Doesn't work that way, however, because there is just a coincidence of numbers here. Okay, so before I explain why this prompt shock doesn't explode the star, I should probably go back because there was a question on neutrino trapping. So to repeat this argument that I made before, so at sufficiently high densities, the neutrino interaction cross sections become so large that the mean free path of the neutrinos gets much longer, much shorter than the core size, and the diffusion time gets much longer than the free fall time. Yeah, so the neutrinos don't get very far; they just scatter around. Yeah, on with a very short mean free path, and that means they're going to be trapped in the local fluid material from which they came from. Yeah, and they're going to be dragged along with the matter in which they scatter. Yeah, that's what this means. They don't escape from a local fluid element anymore. Okay, there's actually another question: is the bounce due to neutron degeneracy pressure? Yes, good question. You might think so, but if it was just the neutron degeneracy pressure, you wouldn't get a very strong bounce. You might not even stop the star from collapsing at all. So the repulsive interactions between neutrons and protons and each other are really responsible for the bounce. You don't do that by neutron degeneracy alone. So neutron degeneracy alone could not support very massive neutron stars. Yeah, the actual repulsive nature of the interactions is important. Okay, that brings us back to the shock wave launched by the bounce. The shock wave launched by the bounce actually does not explode the star. The reason for that is that as this shock propagates through this outer material from the iron core, that material is shock heated and you dissociate that into neutrons and protons. That uses up a lot of energy. It uses up of the order of 10 to the 52 ergs per solar mass. So if you form your shock wave very far inside the core, yeah, at a mass coordinate of about 0.5 solar masses, you'll have used up all of that kinetic energy long before the shock wave reaches the edge of the iron core. There's also another effect that comes into play. So once the shock wave again proceeds to relatively low density material where the neutrinos can stream freely, then those in that material behind the shock wave will immediately cool very strongly. It will immediately emit neutrinos very strongly because that material has the same number of neutrons and protons initially, but it's energetically much more favorable for it to have low electron fraction, to be in what's known as beta equilibrium, yeah, where the chemical potentials of the neutrons are the same as that of protons and electrons combined. And that's a very neutron-rich condition. So to get there, you radiate away lots of electron neutrinos, and that also drains the shock of energy once the neutrinos can escape. Yeah. So both of these effects are responsible for stalling the shock, as we say. Yeah. And this sudden re-emergence of deleptonization, because neutrinos can get out, will actually produce a very, very visible peak in neutrino emission. Well, visible not with a naked eye, but with neutrino detectors. You get very high neutrino luminosities, about 4 times 10 to the 53 ergs for a few milliseconds. Not nearly all of the binding energy of the neutron star yet, yeah, but still a lot of energy that drains the kinetic energy of the shock wave. Okay, the shock wave, however, so the shock wave doesn't just stop there. What happens instead, it's still driven out passively, as it were. So in astrophysics, we speak about an accretion shock. So matter still keeps falling on through the shock, and it keeps piling onto the neutron star, and the neutron star and the shock might adjust to a radius corresponding to some form of effective hydrostatic equilibrium between 50 and 200 kilometers. Yeah, but the matter behind the shock is not expanding. That's what we say, what we understand as an accretion shock. Yeah, so you'll get a situation where you have the core of this young, we can now call it proto-neutron star, within a region of 10 to the 15 kilometers, supported by nuclear repulsive interactions. Around that, you have a layer, so you'll have a sort of extended bloated layer, which we call the mantle, of moderately high entropy. This is stuff that was shock heated by the initial shock wave from the bounce. This is slowly cooling by neutrinos. A bit further out, you then have a cooling region where the material is very transparent to neutrinos, and you basically rapidly cool any material that settles onto the neutron star. That's known as the cooling region. And eventually what emerges, we'll actually analyze why that happens, is a so-called gain layer further out between this proto-neutron star surface and the shock. So in this gain layer, the neutrinos that are still coming out from the region below on average, deposit some of their energy by, well, happening to be absorbed by neutrons or protons. The cooling of this region by neutrino emission still happens, but it's subdominant to this heating of neutrinos that's provided by the neutrinos that are coming from below. All right. Should maybe explain the structure of the neutron star at this phase a bit more in a diagram. So you'll have a neutron star core that's sitting above nuclear density here, yeah, very compact. Outside you have a mantle, yeah. You'll actually see that the temperature has an off-center maximum. That's because this mantle region here was heated by this prompt shock, the shock from the bounce. Yeah, that's why everything's becoming a little hotter in here than inside. Further at the neutron star, proto-neutron star surface, you have this cooling layer. So in the cooling layer, the stuff that that's falling in basically settles to something like a radiative equilibrium temperature. Yeah. So cooling of the material almost balances the heating of neutrinos that's coming from below. That still results in net cooling on average, yeah, because you always supply this cooling region with fresh material, so it always needs to lose energy in the net budget, yeah. And further outside, you have a region that's mostly supported, where you're mostly supported by radiation pressure from both photons and electron-positron pairs between the neutron star surface and the shock. Yeah, this is always rather well described by power laws for the density, pressure, and temperature. Yeah, and further out you have the shock. You actually see you have a jump of the material, density of the material that's falling in. So matter is really moving from right to left in here. So stuff that's falling onto the shock gets compressed here and heated here. Yeah, and then it goes through this heating region and eventually then to the cooling regions where it cools and it settles onto the neutron star. Okay, I mentioned heating and cooling already quite a bit. Yes, there might be questions about that. Those will be answered more fully later. So why is there actually heating? Why does the neutrino emission win in some region? You'll get some quantitative arguments there. But I should probably stop here for another few seconds to allow questions. Questions? Why does the shock get stalled? Yeah, I should maybe repeat that. So the shock stalls. It initially has kinetic energy from the rebound of the core, but as the shock propagates, it needs to dissociate the material that it's running through. Yeah. And that takes a lot of energy, 10 to the 52 ergs per solar mass, a bit more than that. So the kinetic energy will be very quickly drained, and that's why the shock stalls. Okay. Yes, good. So we're left with a stall shock wave here shortly after the formation of the proto-neutron star. We know that that massive stars explode in nature. So why do they explode? Well, you basically have, you can think of two ideas. You somehow need to either deposit thermal energy here behind the shock, or you need to apply sufficient pressure or stresses here to help the post-shock matter drive the shock outwards. Yeah, there are several scenarios have been discussed in the history of this research on supernovae. I'll focus on the two most important ones, two most popular and best explored ones. The first of these is the neutrino mechanism. neutrino-driven mechanism. So here, as I already alluded to a bit, the idea is that you have neutrinos that come from the cooling layer of the neutron star, proto-neutron star surface. A small fraction of those interact, deposit energy into this heating region. That increases the thermal pressure, and the increase of the thermal pressure makes the shock wave expand. And when the shock wave expands, you actually get a larger heating region, and the accreted material has more time to stay in this heating region. Yeah, so the heating will actually get stronger. You get a positive feedback cycle, and eventually that drives runaway expansion of the shock. The other very well explored, or quite well explored idea, is the magnetohydrodynamic mechanism. Here, the idea is basically that you have, say, the proto-neutron star might be rotating very fast. So you have a lot of rotational energy that you can tap in principle. How do you get that out? Well, you could get that out if this rotation generates magnetic fields, and the magnetic fields, by means of magnetic stresses, then additionally support the matter behind the shock, maybe in specific directions. Yeah, maybe this happens more in the shape of bipolar explosions. But the basic idea is you have rotational energy in the proto-neutron star, or perhaps in a disk around the proto-neutron star, or a black hole if your neutron star becomes too massive. You tap that rotational energy with magnetic fields, and the magnetic fields deposit energy in the region behind the shock and drive some form of outflows. Yeah. Okay. We'll mostly focus on the neutrino-driven mechanism in this lecture here. You can do in the tutorials a few analytic estimates of what might be needed to make the magnetohydrodynamic mechanism work. We believe that this doesn't happen in the majority of cases because we think that most supernova progenitors do not have cores with rapid rotation to allow this. All right. Then let's maybe get a few ballpark numbers for the situation that we're dealing with. That's always useful to know. Yeah. So let's look closer at the structure of the neutron star core. So as I said, the neutron star core sits at supranuclear densities. That's several 10 to the 14 grams per cubic centimeter. This energy is of the order, kinetic energy, the internal energy is of the order of the potential energy of the in that region. So the temperatures are large there. You also have neutron-rich matter, but actually the matter is very much out of beta equilibrium, very much more protons than there should be, yeah, in equilibrium. And the neutrinos remain completely trapped there for the duration of the, let's say, interesting hundreds of milliseconds for the explosion. They get out on much longer timescales, so timescales of several seconds. Over those timescales, the neutron star will cool. They will only, the neutrinos from there can only start to escape at densities of less than 10 to the 14 grams per cubic centimeter. For that reason, they actually escape with mean energies that do not correspond at all to, let's say, the energy scale for the center of the neutron star. So they escape with temperatures of a few MeV or energies of the order of 15 to 20 MeV. Yeah. And in a sense, the neutron star core is important. So it doesn't interact a lot with what's happening outside. It does provide a few neutrinos that diffuse out, yeah, and it does provide a boundary condition for the accretion flow onto the core. Yeah, but other than that, what happens in the core is in some sense relatively unimportant. So how the nuclear equation of state looks precisely that has an indirect effect through the boundary condition for the accretion flow. Yeah, so basically through the neutron star core radius. All right. Now, how do the neutrinos escape, and how many of them do we have? So we make electron neutrinos and heavy flavor neutrinos by different mechanisms. So the electron neutrinos and antineutrinos primarily come from captures on protons and neutrons, charged current, and they are primarily coming from this region here, this cooling region here. Yeah. This is different for the heavy flavor neutrinos, which need to be produced at considerably higher densities. Yeah. So in this cooling region, you make electron and neutrinos and antineutrinos, and you power them basically by the accretion power of the material onto the proto-neutron star core. Yeah. So you can estimate their luminosity quite well as the potential at the edge of the neutron star, yeah, potential in the cooling region times the mass accretion rate into the cooling region. For the heavy flavor neutrinos, it's different. So those are primarily almost invariably produced, almost, I should say, by some form of pair processes. So this can be Bremsstrahlung, this can be pair production from electron-positron annihilation, or also from the annihilation of electron neutrinos and antineutrinos. These have a steep temperature dependence. Yeah, and Bremsstrahlung also has a density dependence on rho squared. And for that region, you only produce them at relatively high densities deep inside here. Yeah, so you can produce them in this mantle region in regions of the order of 10 to the 14 grams per cubic centimeter, or maybe a little less. And their luminosity is basically dictated by the temperature in that region and the radius of that region following the Stefan-Boltzmann law. All right, so how does that affect the dynamics? So the heating in the gain region is important, as I said. Let's now discuss why a heating region emerges in the first place. For that, we need to consider basically how the cooling rates and heating rates will scale with radius. So I already explained that in this region behind the shock, where the equation of state is dominated by radiation pressure, what emerges is an adiabatic stratification, where the temperature scales with 1 over radius. Now, the charge current rates, if you put in the scaling of the charge current heating and absorption rates with temperature and electron and luminosity and mean energy, you find the cooling rate scaled with r to the -6, and the heating rate, which heating rate scaled with luminosity times electron neutrino mean energy over r squared. This F thing here is a flux factor that relates the flux of neutrinos to the energy density that will be of order 1. So the heating rate will scale with r to the -2, whereas the cooling rate scales with r to the -6. Yeah. So the cooling drops more rapidly than the heating. That's why heating rate eventually emerges behind the shock. Yeah. Okay. Now we can estimate how much. So does more neutrino heating really change anything in the accretion flow? And to understand roughly what's going on, it's again very useful to just make a simple argument of scales. Yeah. So you can basically argue that if in this heating region, as material is accreted, it's heated so much that the heating zeros its binding energy. So you input the binding energy of the material as it goes through the heating region to make it unbound, then something will happen. Yeah. So if you pump so much energy into the matter that you make it unbound, then something will happen. It will no longer accrete onto the proto-neutron star anymore. Yeah. So you can estimate how close you get to that critical limit by considering, well, how long does the material spend in the gain region? That's called the advection timescale. And what's the time that you need to heat the material to make it unbound? That's what we call the heating timescale. So this is basically the binding energy in the gain region divided by the heating rate. Yeah, and when the advection timescale is longer than the heating timescale, you'll heat the material in the gain region enough to unbind it. Yeah, and then you get continued expansion of the shock. The shock will have to adjust then, and conditions will become even more favorable for neutrino heating, and you'll get runaway expansion. So we won't do a full calculation there, but you can put the expressions for the rate laws together. You can put a solution for the quasi-hydrostatic accretion flow together, and then derive a scaling relation for this critical ratio, advection timescale versus heating timescale. Yeah, and you'll find that this becomes larger with neutrino luminosity and mean energy, and the counteracting effects are basically a higher accretion rates. And there is also some dependence here on the mass of the proto-neutron star inside and the radius of the gain region, inner radius of the gain region. So if the luminosity becomes high enough, basically you get into a regime where stable accretion is no longer possible and the shock has to expand in a runaway fashion. Yeah. All right. Now, how can we achieve this? So if you wanted to put more concrete numbers on this and also estimate a bit how much energy, how much matter you can then inject by neutrino heating, you can again look at some, it's again useful to look at some ballpark numbers. So the specific binding energy of material at the gain region is of the order of a few tens of MeV per nucleon. The electron antineutrinos and neutrinos, those are the ones that really contribute to the heating, are of order 10 to the 53 ergs. You can only use about 10%, only about 10% of that will interact while crossing the gain region. So that puts your energy budget down to 10 to the 52 ergs. Yeah. Now suppose you heat for about half a second. Yeah. That number now comes from somewhere. You could actually string together some arguments for that as well. And you say, well, how much energy, how much material can you unbind? Then you find, well, maybe you can unbind about 1/10 of a solar mass of neutrino heated material. Okay. Now the neutrino heated material, the neutrino heating will just unbind the material. Yeah. So if you've unbound the material, just unbound the material, you've already used up your energy. So it would just go out further and sit there and asymptotically have zero velocity. Yeah. So that's not enough. What we find in simulations actually powers the neutrinos eventually, the explosion eventually, is really the nucleon recombination, the residual nucleon recombination. So the neutrons and protons that you've driven out by neutrino heating, they will recombine into alphas and maybe to some extent into ion group nuclei. So you release a bit upwards of 5 MeV per nucleon. Yeah, And that then gets you to an energy budget of the order of 10 to the 51 ergs. Yeah, so that's roughly explains why we get to explosions of order 10 to the 51 ergs in the end. Now, does that mechanism work? Well, difficult question. So in spherical symmetry, so if you assume that this infall and explosion are all spherically symmetric processes, this fails for most supernova progenitors if you treat this neutrino heating and cooling correctly. Yeah, the exceptions are just the very lowest mass progenitors. We discussed this channel of electron capture supernovae yesterday. The reason is that here the accretion rate drops very rapidly due to the density structure of the core. And for that region, it becomes very easy to get an explosion going. Yeah, but in most other cases, what you need are multidimensional effects to make this mechanism work. Yeah, so why do multidimensional effects come into play and why are they useful? So what you'll have in this cooling region is as matter goes through the cooling region, you're heating it. Yeah, so you'll be the material as it at the bottom of the cooling heating region will be hotter than at the top, and hotter in terms of entropy, not in terms of temperature. Yeah, terms of temperature as well, but it's the entropy increase that counts. So if you have such a situation where the entropy inside is higher than the entropy outside, this is going to be an unstable situation. So this can power convection. And what convection does is, you can think of it this way: you have heating, the heating makes, well, a bubble of slightly buoyant material makes that expand. Yeah. So you convert the heating as a buoyant bubble expands into kinetic energy by PDV work. Yeah. And in the end, of course, as this bubble at some point dissolves, the kinetic energy is put back into thermal energy also by turbulent dissipation. Yeah. So you can work out then how this balance between energy injection and conversion into kinetic energy and dissipation, how that plays out in the end. It will basically lead to convective motions that are stronger the more neutrino heating you have per unit mass in the gain region. And what the effect of that will actually be, we'll figure that out in a few minutes. The effect of that will actually be that this, well, on the one hand, this dissipation then provides additional thermal pressure closer to the shock. And on the other hand, the convective bubbles, as they're bumping into the shock wave, they're effectively exerting some form of turbulent pressure as well. Now, another sort of non-radial flow that probably plays a role in supernovae according to our current theory, this is known as the standing accretion shock instability. Yeah. So this is different from convective flow. It's a phenomenon where where something actually happens that's very similar to the physics of a boiling kettle. So you get at the shock wave, a slightly distorted shock wave, you generate slight perturbations to the flow, pressure perturbations, but more importantly, vortical perturbations, lateral flow, yeah, sometimes going to the left and right. And as those flow perturbations hit the neutron star surface, they're converted into pressure waves, acoustic perturbations that go out to the shock, and that can lead to an amplification cycle. Yeah. This has a very peculiar flow morphology, very funny flow morphology. It gives you large scale oscillations of the shock during the linear stage, and eventually saturates as well. Quite interestingly, you can visualize that also in an laboratory experiment using an analogy of the equations of fluid dynamics to the equations for shallow water. My good colleague Thierry Folizzo has made an experiment with an analogous instability in shallow water. What you have here basically is matter, well, in that case, water flowing in, injected at this ring outside into a funnel. So it's actually deeper inside here. And inside you have this tube here, which sticks out a bit. That's the neutron star. That's stalling. That's breaking the accretion flow into this funnel, as it were. And then that flow results in these global oscillations of the analog of the shock wave. This is technically called a hydraulic jump here. So the water level, as you see, is a bit higher here. Yeah, that's the analog of our shock wave here. And that starts to wobble around in a spiral pattern. And you actually see that the shock radius is increasing. Yeah, so you have a similar effect. These non-violent fluid motions exert effectively some form of turbulent pressure as well that can make the shock wave expand. Now, next I'm going to show you how this looks in a real supernova simulation in 3D, these two instabilities. So this was many years ago for a 27 solar mass star. You just saw the neutron star forming here. The translucent blue surface is the shock wave. Then a while after the neutron star is formed, you develop convective bubbles, yeah? And then very shortly, you'll see these large-scale shock oscillations appear. Yeah, you see them now. And then the shock expands quite a bit. We're going to rotate this structure. And unfortunately, in this particular model, we found that the shock then again retracts as we continue this, so we did not actually get an explosion. Okay, I'll let this play here. All right, yeah, so you see the shock has retracted again, a little neutron star inside. And after a while, the standing accretion shock instability starts again. Yeah, good. All right, now let's ask though, why are these effects actually helpful for making the star explode? So I gave you the qualitative explanation already in some form. The key thing is really that there's a variety of effects coming into play. So on the one hand, these non-radial motions provide effective turbulent pressure. We also call that Reynolds stresses. And they also help mix the hot material at the neutrons closer to the neutron star with the colder material further out. And the dissipation also increases the thermal energy of the material behind the shock. All of that basically increases the pressure support for the shock, and that is helpful for making the shock expand. You can combine that with this estimate for the advection to heating timescale ratio that I mentioned before. And what will basically happen is that the effect of the turbulent motions is to increase this timescale ratio, criticality ratio, by a factor that is related to the turbulent Mach number of the flow, whether it comes from convection or this standing accretion shock instability, SASI. So the more violent these non-radial motions, the higher the ratio, the odds of getting over this criticality threshold, advection time scale larger than heating time scale. Yeah, so the key is, in a sense, to have violent non-radial, non-spherical motions that support the expansion of the shock. We have actually checked quantitatively whether this relation describes the physics of supernova shock revival, and it actually does a quite good job at that. Now, in recent years, we've recognized that there's one very interesting means to boost these non-radial motions behind the shock, which makes an interesting link to the evolution of modeling of supernova progenitors. So I explained to you yesterday already that, well, the convective burning shells of stars before collapse are maybe not so spherical at all. Yeah, there can be violent spherical motions at play there, with velocities of hundreds of kilometers per second. And then what will happen as these shells collapse and fall into the supernova shock, these will result in quite significant perturbations of the pre-shock density and pre-shock ram pressure. And that will make it easier for the shock to expand in certain directions. Yeah, so the shock will have an easier time expanding in directions where the ram pressure is low. Yeah, and that sort of guides the expansion of the shock and facilitates it on average, giving rise to what we know as perturbation-aided explosions that can result in significantly easier explosions than you would have if you just let spherical progenitors collapse. Good. Now, given how we're progressing in time, I think what we'll probably need to do is I will again run over. Yeah, we have about 10 minutes left, right? And I should probably, so you want to see a bit about numerical modeling, but I should probably have maybe a section on that tomorrow to prepare you for the
Yeah, you have about 10 minutes, as you said. Sorry.
Tutorials, yes. And maybe we'll skip ahead now through this rather technical part. That's something that is digested badly at the end, and we'll first finish what modern explosions say. Have a look at that. And I'm sure I can fit in the numerical modeling at some stage. So maybe I'll spend some time on that tomorrow. Let's see how that goes. The upshot, though, is that if you put all the ingredients together that you now need to model supernova explosions rigorously, instead of just throwing around a few order of magnitude estimates as I have done, what you basically need is, well, you need to put together the equations of fluid dynamics, conservation of mass, momentum, and energy. You need equations for the transport of neutrinos, and you need an equation or equations to describe the gravitational field. And in principle, since neutron stars are very compact objects, you need to do this in a general relativistic version. We're not going to discuss that today. Yeah. Then you put that together, perhaps even adding magnetic fields, and you see what comes out. Yeah. So let's first see what comes out. So the interesting or the encouraging results nowadays is that we can routinely do 3D simulations with neutrino transport, resolving the neutrino spectra, so treating the neutrinos not as having a Fermi-Dirac spectrum, not as gray transport, but with energy resolution, which is important because the neutrino interactions depend very much on energy. And many groups are now obtaining successful explosion models. Yeah, that has to do with a number of factors. We're running longer simulations. We're realizing that it's important to take into account the non-spherical structure of the supernova progenitors and so on. So we get many groups are now able to produce explosions in 3D models. And let's see how those stack up against observations and against some of the parameters that we can infer from observations. So what is still a bit of a challenge perhaps is to explain by simulations the whole range of explosion energies that we see in nature. But we have in more recent months and years actually been able to simulate some explosions for long enough to see the saturation of the explosion energy. The key problem here is that even after the explosion is initiated, you still get downflows onto the proto-neutron star through these expanding bubbles of convection that still feed neutrino heating and still feed outflows and still pump energy into the explosion. Yeah, that can last for well over a second. So it's very challenging to simulate that process in its entirety. You need to simulate very long timescales. Yeah, second-long simulation in 3D with neutrino transport. That's very expensive. And if you do that, though, you are able to explain nowadays explosions of up to 10 to the 51 ergs by means of neutrino heating. It could still be that we're missing some minor form of neutrino of energy input into the explosions that comes on top of that. But overall, we're not too far. So the values that we see in the simulations, predicted simulations, are not so far from the range of explosion energies that we observe in type 2p supernova explosions. And what we also get, and what is quite interesting, the models, if you look here, they tend to be more energetic for progenitors of higher mass, and that's exactly what we see in observed explosions as well. The reason for that is basically that the amount of energy that you pump into the explosion essentially is related to how much you accrete on the neutron star after the explosion is initiated. Yeah, so we already played that game before to some extent. So we said, well, for each unit of energy by input by neutrino heating, we can unbind so much material, we can obtain such an outflow rate, and then the residual explosion energy will come from the recombination of the neutrons and protons in the outflows. And if you tie that then further to the source of the heating and take into account that the neutrino heating comes from the luminosity, it's a fraction of order 0.1 of the neutrino luminosity, and the luminosity is largely given by the mass accretion rate onto the neutron star times the gravitational potential at its surface. You basically get to the point that the amount of neutrino heated matter that you eject is proportional to the amount of matter that you accrete times a few efficiency factors. And you can then get that in a similar manner from the for the explosion energy. And it basically turns out that the more mass you accrete onto the neutron star, the more energetic your explosion becomes. Now, how long does this accretion last? Well, basically it lasts until your post-shock matter gets ejected so fast that it doesn't fall back onto the neutron star anymore. Yeah, that happens more easily in low mass stars because there's less, the shock is facing, as it were, less resistance. It's running into less dense material around the iron silicon core. And that's why in low mass stars, accretion stops earlier and you accrete less than in high mass stars with more massive cores, more compact cores. Yeah, so this qualitatively explains, and that's perhaps one of the most important accomplishments of models of the neutrino-driven mechanism, why we see observationally a correlation between neutrino, between the progenitor mass and the explosion energy. Okay, now on to alternatives very quickly. So as I said, the neutrino-driven mechanism is not the only mechanism that might operate in nature. There are some explosions that we observe which seem to have energies of 10 to the 52 ergs. So it's hard, given those efficiency factors here, it's hard to obtain explosions of 10 to the 52 ergs with neutrinos. Maybe should go further and say it's basically impossible. So people are looking for extra energy sources to explain those explosions. And one of those ideas is basically that you tap the rotational energy of a millisecond neutron star with millisecond rotation periods. Yeah, that would give you enough energy to power these explosions. And the idea is that you convert that part of that energy into magnetic fields. Yeah, not all of it, just part of it, just enough to efficiently transfer rotational energy from the core into energy in outflows. Yeah, and that then gives rise to these powerful explosions. And models indicate also in agreement with theoretical expectations and in agreement with observational findings that these would be very asymmetrical bipolar explosions. Now, what will happen on much longer timescales? Well, the aftermath will be once you have your explosion triggered and you've put about 10 to the 51 ergs of energy into the explosion, the shock will still have to run for sometimes hours, sometimes also minutes if you have a very compact progenitor through the stellar envelope until you actually see it breaking through the surface and the stellar surface becomes bright and you actually have an observable supernova explosion. Yeah, that will give rise. So in the process, you'll still have a lot of hydrodynamic phenomena going on, a lot of mixing instabilities going on that will then shape what you actually see in the spectra. The long-term evolution of the asymmetries in the explosion will also affect whether your neutron star is bumped around in the explosion and leaves it with a considerable kick. Some of the later lectures will still address that. And yeah, that's the aftermath, which is more connected to the phenomenology of supernovae and compact remnants. We'll get to that later during that course. And here we are at the end and have now, and hopefully now you understand this overall physical picture of what happens between collapse and explosion. As I hinted at, we had to skip in the interest of time this section on modeling. I will go through that hopefully briefly tomorrow and give you enough of an introduction to actually be able to do the tutorials. Yeah, and now let's maybe have some questions.
Thank you, Bernhard, for this overview. So any questions for Bernhard?
Yeah, so I had a question. So in your in the last panel, which says neutrino cooling and neutrino driven wind, this our process question mark.
Yes.
So I thought our process was not very efficient in supernovae, and
yes, it isn't. That's why there's a question mark.
Okay.
Yes.
Is it just because there's not enough energy?
The reason is, we'll come to that hopefully on Thursday. The reason is that the electron neutrino luminosities and mean energies and the anti-electron neutrino luminosities and mean energies are very similar in current supernova models. And that implies that the outflows that you launch from the neutron star will be proton rich and not neutron rich. Yeah.
Right.
And if they're proton rich, then you can't make an R process.
Okay. So I had another question about the magnetohydrodynamics slide.
Yes. Yeah.
So yeah, I mean, so you said there'll be polar supernovae. I mean, this
bipolar. Yes. Yeah.
Yeah. Right. So there's be, preferential ejection of material in one direction. So is
Yes.
this, and you said that we have observed such supernovae, is that right?
Yes, we observe them, and we see the strong bipolar asymmetries. We can infer that from polarization signatures.
I see. So yeah, okay. So the polarization measurements as well. Okay.
Yes. Okay, further questions?
Any other question? Bernhard, I had a question for you.
Yes.
How sensitive is this to the neutrino physics? Like, for example, the mass of the neutrino and so on?
Ah, yes, that's a very interesting question. So it's sensitive to the neutrino physics. So physics parameters, you'd have to tweak them quite a bit to do something really crazy. Yeah. So if you had a light sterile neutrino that could do, in the right mass range, that could do very strange things. It might kill this whole scenario. There are hypothetical parameters where you can kill the whole scenario. That's quite unlikely though. But there are a lot of uncertainties about the neutrino interactions that are very relevant to how well the explosion mechanism works and how energetic these explosions become, how easy shock revival is. And there is something of a big unknown in how neutrino flavor conversion unfolds. I hope to cover that tomorrow a bit. It's an unsolved question. Neutrino flavor conversion is complicated in supernova interiors because the scattering of neutrinos off each other, forward scattering, creates something similar to the MSW effect, but much more complicated because the interaction is nonlinear, and you can get some certain collective oscillation phenomena. There is, I think, founded hopes that this will not change the dynamics of the explosion too much for several reasons. One reason is that the electron, neutrino, and electron flavor and heavy flavor emission is not so dissimilar to begin with, but still, this is the quantitative effect is not sorted out because this thorny problem of collective flavor oscillations is not fully solved.
Thank you. Any other question? Going once, going twice. Bernhard, thanks.
Okay, good.
Meet tomorrow.
Yes, so then tomorrow I hope that I can still make up on this section on numerical modeling, and then proceed to gravitational waves and neutrinos. If there is any interest, I mean, I have probably prepared a little more material than we can cover in total during the course. If you want to organize some spillover session, I'm open to that. We could arrange that. Okay. Anyway, I'll see you tomorrow and have fun in the tutorials.
Bernhard?
1 second. Yes.
Yeah, if you want to take some part of the tutorial to cover the remaining section, you can do that.
Okay. Should we already do that today?
Yeah, I think it should be fine.
Yeah, it should be fine because I think it's actually not so long. Yeah.
Yeah, and anyway, we have 2 tutorial sessions, so you can take some part of the first tutorial and then we'll do the tutorial problems after that.
Okay, so let's start. Thank you for this opportunity to wrap up the discussion of numerical modeling in the tutorials. This will, I hope, be some good preparation for the tutorial problems that I had included on this. So as I indicated in the main lecture, if you actually want to model supernova explosions or really any astrophysical phenomenon quantitatively, you need to usually resort to numerical simulations. And in the case of core collapse supernovae, that means you need to include the conservation equations that describe the fluid dynamics or perhaps magnetohydrodynamics, the equations for the gravitational field in whatever approximation or exact version for general relativity that you decide, and equations for the neutrino transport in this particular problem. Now, the equations for neutrino transport are probably the most complicated ingredient in this whole game, because neutrino transport is a problem in kinetic theory. Yeah. This means that we need not only describe the distribution of neutrinos in real space, as we would for the fluid. So fluid is described by density, momentum density, and energy density as a function of spatial coordinates. We also need to take into account the dependence on phase space coordinates, momentum space coordinates. And that, of course, makes the problem, doubles the dimensions of the problem. Yeah. So the transport problem in its full beauty is a 6-dimensional problem. If you were super punctilious about it, it's actually a 6-dimensional quantum kinetic problem if you account for flavor conversion as well. Now, let's focus, however, on the simplest possible case of kinetic theory, which is the kinetic theory in the Newtonian approximation, and that's described by the Boltzmann equation or transport equation. Yeah, and the Boltzmann equation is essentially a conservation equation in phase space, which says the phase space density of particles is conserved along the trajectories in phase space. That's follows from Liouville's theorem. And added to that are source and sink terms and redistribution terms on the right-hand side that account for absorption or emission or scattering of particles. That's what we call the collision term. Okay, maybe I should allow for questions right here because some people may not have encountered the transport equation yet. So maybe any questions on that before we proceed?
Hello.
Yes.
Can you reiterate on how the collision term would look like?
Oh, yes, that's going to come on the next slide. That's going to come on the next slide. So maybe you bear with me for a second about that. Any other questions? Yeah, so before we proceed into looking into seeing what actually has to enter in the collision term, I should say that this is the simplest possible form of the transport equation, or almost the simplest possible form. The transport equation becomes very complex if you allow for general relativistic effects to come into play. A lot more terms will pop up. You might simplify it a little more in the Newtonian case if you measured the momenta of the particles that are of interest. So in our case, neutrinos, if you measured that in a fixed inertial reference frame, that's also a global inertial reference frame. So in the same frame of Minkowski space-time, yeah, then this term here would drop out, because in that global reference frame, the derivative, time derivative of the particle momenta would be 0. But a term like this will very soon pop up as soon as you start to measure the particle momenta in different frames. For example, in what's known as the comoving frame, which moves along with the fluid, that's going to provide the background for the interactions of the neutrinos. That's a useful frame to adapt to, because in that frame, the collision term will take its simplest possible form. And as soon as you move to the co-moving frame, this term here that accounts for changes in the particle momentum as the particles propagate, as soon as you go to the co-moving frame, that term will always reappear. Yeah. And I should probably preface all of this discussion by saying the aim here in the tutorials will naturally not be to write a supernova neutrino transport code. If you can do that in an afternoon, you deserve a Nobel Prize. That's way too complicated. But I'd like you to understand some basic difficulties that often pop up in the treatment of radiation transport, and whether you're doing radiation transport in supernovae, or whether you do that in neutron star mergers or in star formation, whatever stellar atmospheres. As you move along in your career, you might find some of these things useful. Now let's look at the collision integral, what actually has to go in there. So in the collision integral, what modern supernova simulations tend to include are a number of absorption and scattering reactions, starting with electron captures on nuclei or on nucleons, scattering, one part scattering of a neutrino of a neutron, proton, or nucleus is the simplest possible case, quite easy to treat. Even there, some problems start to come into play. If your neutrons and protons are interacting with other neutrons and protons, then you get many body effects that complicate the whole thing. Neutrino scattering on electrons starts to become a bit more complicated, because that is always associated, or almost invariably associated with a change of not only a change of direction of the scattered neutrino, but also a change in its energy. Yeah, unless the scattering geometry is very fortunate. That makes things more complicated if particles scatter and not only change direction, but also energy. To some extent, that also comes into play for neutrino nucleon scattering already. And then you have some processes which are probably the most nasty ones to treat, which involve pairs of neutrinos created by electron-positron annihilation or Bremsstrahlung or neutrino pair conversion. And what makes these processes, in particularly nasty is that, well, you always have to solve coupled equations for the neutrinos and their corresponding antineutrinos. You actually couple the neutrinos and antineutrinos in all directions, all different directions and all different energies. That makes for a very nasty nonlinear algebraic system that's not very well conditioned and costly to invert. And in neutrino transport, unlike, for example, in photon transport, further complication is that final state blocking actually plays a role, because neutrinos are fermions. Usually we wouldn't care about that in the case of neutrinos, because we rarely have such a dense neutrino gas to deal with as in supernovae. That's where the blocking actually starts to count. That complicates all of these interaction terms a bit, but it's probably especially nasty for these various pair processes that couple every neutrino energy and momentum with every other, the density of neutrinos, phase-space density of neutrinos of every other direction in energy. Yeah, because of the sheer number of processes, and because some of these processes are reactions of not just a single neutrino, it would actually be incredibly tedious to write down closed expressions for all of these. I actually won't do that here because it becomes very complicated with some high dimensional integrals, especially for these pair terms here. And instead, in the exercises, we're going to focus on very simple terms for the source term instead, that illustrate basic principles. Now, one of the basic principles that, that matters a lot is that these interactions have timescales that are often, especially inside the neutron star, much shorter than the dynamical timescales. Yeah, they can be orders of magnitude shorter than the dynamical timescales. And in terms of the numerical treatment, that means that these source terms for neutrino interaction, source and sink terms, are what we call stiff. Yeah, so they will drive the distribution function to an equilibrium very, very, very quickly. Yeah, and you might think that's an advantage if you can easily apply some form of equilibrium, thermal equilibrium approximation. But if you want to consistently treat the interactions in a regime where they're in equilibrium, and when they're not in equilibrium, and you're using the same method to evolve them dynamically in time, then that method tends to become very ill-conditioned, and the numerical solution becomes complicated. Now, there was a question in the chat about what coherent scattering of nuclei means. I think I already hinted at that in the main lecture, but let me maybe just redraw this. So when we're talking about coherent scattering, as opposed to incoherent scattering, the phenomenon that we encounter is this. Yeah. So suppose you have neutrons and protons around here at relatively large distances, and the extent of the neutrino wave package, or its de Broglie wavelength. Yeah, so you have a neutrino wave packet here. Yeah, and you send that across through nuclei that are at sufficiently large distances to each other. What will basically happen is that the cross-section, the overall cross-section, will scale with the number of scatterers. Yeah, so the number density of neutrinos and protons. Yeah, that sounds reasonable. Yeah, so the more neutrons and protons you have, the higher the chance that you scatter, and the chance of scattering overall, which gives you a cross-section, that's proportional to the number of neutrons and protons. Yeah, but so this would be incoherent scattering. Yeah, but the thing is, if you now have neutrons and protons in a nucleus, yeah, then what will actually happen if you send a wave packet of neutrinos onto this nucleus is you really have to sum up the amplitudes of the Feynman diagrams for the relevant scattering amplitudes. So we write coherent scattering here. So what you'll have to do is you'll have to sum up amplitudes. Yeah. So you sum up the amplitude of neutrino scattering of neutron 1 and neutrino scattering of neutron or proton 2. Yeah. Plus all other combinations plus permutations from quantum statistics. Yeah. So the summation has to take into account that these nucleons are, of course, indistinguishable. Yeah. And the result of that will be, yeah, that your cross-section for an individual nucleus, so for one nucleus, will be proportional to A squared. Yeah, essentially, yeah, you can. I'll do an explanation of how this can happen for photons as well. Yeah, and your overall opacity, which is cross-section times number of scattering times the scattering cross-section. So let's say this here, number of scatterers times scattering cross-section. That will be proportional to matter density divided by the average mass number of the nucleus times the cross-section, which will be proportional to mass number squared. Yeah, so you get an extra dependence of the cross-section on the average mass number of your nucleus that you scatter on. In reality, it's a little more complicated because the neutrons and protons aren't the same two weak interactions. Yeah, so it's actually the neutron and proton number that has to enter here separately with a few weak interaction coefficients. And you might know actually a very similar phenomenon for electromagnetic scattering. So basically what you get in electromagnetic scattering as well, if your scatterers for a light wave are distributed such that the wavelength is long, yeah, then what will happen is that the scattered waves will add coherently. Yeah. And your cross-section, so the average energy, which is or the average energy of the scattered light, or the flux of the scattered light, which would be in terms of radiation transport theory related to the opacity, that would behave with the square of the number of particles that interact coherently with the wave packet. Yeah. And the square simply comes about because, well, if you add n times some amplitude, some scattering amplitude, and you square that, yeah, this is the same as multiplying the square of your scattering amplitude for an individual scatterer with n squared. Yeah. So it's a very similar phenomenon as what we have in electromagnetic scattering. The waves of various scatterers adding coherently, and that leads to an amplification of the scattered wave overall, which goes with the square of the number of scattering targets. Okay. Self-interactions of nucleons in the scattering process. There was a question, are we ignoring that? photons in this case? Okay, actually two good questions here from the chat. So someone asked what happens to the interactions of neutrons and protons with each other. Yes, in the 0th order approximation, you might ignore those and only take into account that they will at least undergo Fermi blocking in some, and include correction factors for that. But in the most accurate treatment, you need to take into account that there are interactions between the neutrons and protons, and these will need to be fed into these absorption, emission, and scattering rates. Yes. And there was a question about photons. So the photons luckily don't concern us in the supernova case in the core, because they are tightly coupled to the rest of the matter. So they are always in thermal equilibrium, and they don't interact with the neutrinos directly. Okay, that was questions. Then there was a question, do we only need to take into account tree level processes? That's a good question. Yes, for some this is sufficient. For others, you need to take in some loop expansions into account, like for Bremsstrahlung, I think. But for the most part, you can get away with tree level approximations. Final state interactions, though, that's always more of an issue whenever you have neutrons and protons involved here. Yes, good. Now let's proceed and ignore or very much simplify the collision term for the time being. So to see how you can get to grips with the full 6-dimensional Boltzmann equation, it's very useful to just simplify, start with very simple approximations for the collision integral, where you basically just say the collision integral is going to be something like an opacity times
Hi. You're not sharing your screen. We cannot see anything.
I'm not sharing. Did I stop that? Did you see it before? Yes.
Yeah.
So to start with the simplest possible form of the collision integral, what you can do is so focus on absorption and emission processes, which can be written like this: an opacity times the deviation of the distribution function from thermal equilibrium. Yeah. This will always drive the distribution function to thermal equilibrium. Any absorption, pure absorption and emission process will actually take this form. And for scattering, you make a very simple approximation. So the simplest possible approximation is to treat scattering as isotropic and isoenergetic, which means that you remove with some opacity. So with a probability that scales with 1 over units of length times the length that the particle travels, you remove particles from the beam by scattering, and you add particles that come from other directions and have scattered from other directions. You assume those are redistributed isotropically, and then your collision integral will look like this. Yeah, so you remove neutrinos at a rate opacity per unit length, which is given by the opacity, and the neutrinos that are removed will be redistributed isotropically in all directions. So this will ensure that the scattering terms don't create or destroy any neutrinos in total. Total number is conserved. Now, if we make such an ansatz, this is useful in the exercise that we're going to do next. So because of the high dimensionality of the Boltzmann equation, serious supernova simulations in 6 dimensions are just not possible. And you need to rely on approximations in practice that reduce the dimensionality of this problem. And the most important strategy for that is to develop the Boltzmann equation into a system, into a chain of moment equations by taking angular moments of the distribution function. So integrating them over angle and possibly angle times tensor products of velocity, of the velocity vector with itself. Yeah. So the first moment, or zeroth moment rather, in technical terms, will be just the integral of the distribution function over angle. The next moment will be the integral of the distribution function times velocity over angle. That will give you a vectorial quantity, flux-like quantity. And the next one will be the integral of f times velocity I times velocity j over angle. That gives you a tensorial quantity. Yeah. Now then you can formulate by integrating, taking these moments of the Boltzmann equation, you can formulate equations for these moments, and you end up with a hierarchy of equations. So the first moment will just be a flux balance equation for the neutrino energy density for a given energy group, really. So the standard approach here in supernova simulations is to take a multi-group approach where you distinguish neutrinos of different energy. Yeah, so that would just look like time derivative of the number density in that energy group plus the divergence of the flux in that energy group equals source term minus sink term from absorption and emission. And similarly, you'll get an equation for the first moment in terms of this the divergence of the second moment, and the source and sink term as well, which come both from absorption and from scattering in this case. And with this form of the collision integral, these right-hand sides are relatively simple. Yeah, the general form would be very complicated if you allow for interactions of two neutrinos and the redistribution of energy of neutrinos and non-isotropic scattering and so on. But the basic principles behind solving these transport problems can be seen if you use this simple form of the collision integral. So let's see how we can then somehow make this work. I mean, the problem here is that we still have an infinite hierarchy of equations. Yeah. So the key that we need to apply here is we need to somehow truncate that hierarchy of moment equations. Yeah. And the simplest possible approach to that, which is the diffusion equation, tries to truncate the hierarchy of moment equations basically already after the first equation. Yeah. The way you do this is you say you're considering the case where the interactions are still so sufficiently fast that the equation for the flux is driven into equilibrium on very short time scales. Yeah, and the time derivative of the flux moment, the first moment h, can be neglected. Yeah, so in that case you're just left with this term here, the divergence term of the second moment, and the scattering term on the right hand side. You set those equal, and that gives you an expression for h in terms of the derivative of this second moment tensor. Yeah. If you further assume that the second moment tensor is directly related to your zeroth moment, yeah, and is just isotropic, then this gives you an equation that relates the flux to the gradient of the number density in that energy group. Yeah, and if you've ever encountered Fick's law, that's really just a diffusion equation for this flux quantity Hi. Now you can put this into the equation for the for the 0th moment, and you've closed your system. Yeah. Now, this approximation, however, has quite some obvious pitfalls. So one, what happens if your opacity is 0, right? If you go into the optically thin regime where there's no matter to scatter on anymore, then your flux will diverge, will go to infinity. Yeah. So this is one issue, but there's a less obvious one as well. The diffusion approximation introduces implicitly infinite signal velocities. That's, in a sense, that comes from the fact that you assume that the equation for H, the time evolution for H, immediately goes to an equilibrium solution. And that has repercussions, because that means by so-called explicit solution methods, which just start with the solution at a given grid point and its neighbors, and use no other information, don't use the global information of the solution on the entire grid, you face very serious time step constraints. So the solution becomes very inefficient if your grid spacing becomes very small. The time step goes down with grid spacing squared. So that's a big issue from the point of view of computational efficiency. And in a sense, that means you also have some form of stiffness problem, because the diffusion equation would like to adjust to certain solutions on very short time scales. And if your time step is too small, your diffusion equation will become unstable. Now, one of these problems can be fixed. So the problem of diverging flux in the limit of small opacity can be fixed by introducing what is known as a flux limiter. So you'd multiply the diffusion flux by a factor which ensures that the energy flux can never be bigger than the energy density in that particular energy group. Yeah, that's a consequence of the fact that photons or neutrinos can only propagate at the speed of light. That means that their energy flux can never be greater than their energy density. This is implemented in some supernova codes, but it is, of course, an important approximation. Yeah. Why does this approximation matter? Well, if you look into neutrino heating rates, the neutrino heating rates will be proportional to the energy density, the local energy density of neutrinos, and their mean energy and so on. Yeah. And the energy density is related to the flux which enters the luminosity by a factor F, the ratio of the flux to the energy density. Yeah. So this means that this flux factor H over J enters into the effective neutrino heating rate. Yeah. And there can be quite some significant dependence on the choice of the flux factor and the flux limiter, and the flux limiter will affect the flux factor and hence the heating rate. Yeah. This is an important thing to consider. And for that reason, what many codes have moved to in recent years are so-called two-moment approaches, where you retain one more equation in your chain of moment equations. So you have both an equation that involves an energy density J and a momentum energy flux density HI. In order to do that, you need some plausible assumption for what this second moment looks. Yeah, now you need that to close the system, the Kij. The simplest approximation is the same that we fed into the diffusion equation. So just make this an isotropic tensor. But this is a very limited choice. Yeah, that's only accurate really in the diffusive regime. So that approximation, the so-called Eddington approximation, doesn't get you very far. you can play around in the tutorials with some of its consequences. Yeah, if you use the Eddington approximation in the wrong regime, the radiation solution will do strange things. So you can use more sophisticated closures, and I'll mention to provide the Eddington factor in terms of J and H. I'll show you a few of those later. Now, those moment schemes also have their pitfalls, and I'm asking you in the tutorials to experiment with these as well. Yeah, so these two moment equations give you a system that's very similar to a conservation law, as you're might be familiar with when you're solving the equations of hydrodynamics, a so-called hyperbolic conservation law, coupled with source terms and sink terms on the right-hand side. Those will have nice time step limits. Yeah. The time step limits will be given by the light crossing zone in a time in a grid zone. And that's nice, but this comes at a price, or at the price of a problem. The problem is that the left-hand side and the right-hand side can interact in problematic ways. And if you use naively some method that solves these hyperbolic conservation laws, and then couple that in what's known as a splitting approach with the source and sink terms, then things may go very wrong. So a splitting approach would be to say, I first evolve the equations according to left-hand side equals 0, and then in another step, I add the sink terms and source terms. Yeah, that can have very dangerous consequences. And you're going to experiment with that in the tutorials. Yeah, the reason you might want to split these terms is that these source terms and sink terms on the right-hand side can still be very stiff, so require very short time steps, unless you use what is known as an implicit scheme to solve for them. Yeah, and if you couple that implicit scheme fully with a solution for the left-hand side, then you'd end up with a very big implicit problem where everything is coupled with everything else. So you get a complicated nonlinear algebraic system and need to solve that. You'd rather solve for these source terms and sink terms locally, yeah, and use an explicit method that only requires local information for the left-hand side. But accomplishing that without spoiling the solution isn't so easy. Now, this is not something that you'll remember for long, I guess, but still wanted to mention it. So there are really a number of possible choices for these second moments of the distribution function that have been proposed and are used in supernova simulations. All of these have upsides and downsides. They might be more accurate in one situation than in others. And there's also a more rigorous approach of combining something like a simplified solution of the transport equation with such a two-moment approach. You might think that's overkill, but it can still be an efficient method to actually solve the Boltzmann equation in some downsized form, and then use that in conjunction with moment equations. This is what the vertex supernova code does that I have also worked with quite a bit. Yes, and that's basically what I wanted to say about the treatment of neutrino transport problems or radiation transport problems in general as a background for the tutorials that we have prepared for you. Good. All right.
Thank you, Bernhard. Any questions for Bernhard?
Yeah, Bernhard, how can we sort of quantify the error that is incurred by just using a two-moment approximation and not?
That's a very good. That's an excellent point. Ultimately, you can only quantify the error by comparing it with a more rigorous solution of the Boltzmann equation. That, of course, can presently be done, so have to be precise about what I say, that can be done relatively easily for simple toy model problems. Let's say you have a homogeneous sphere of constant density, constant opacity, and you can use both an exact solution of the transport equation and a two-moment equation and compare them. In supernova simulations, limited comparisons are possible. So it's possible to compare two-moment schemes with Boltzmann schemes in 1D, in dynamical simulations, and there they fare reasonably well most of the time. And there have also been comparisons of transport solutions for multidimensional supernova simulations, but only for static snapshots. Yeah, so you take a snapshot of a simulation and you let the radiation field evolve into a stationary state, and that's something that you can do for Boltzmann transport with grid-based methods, discrete ordinate methods, or Monte Carlo transport as a reference for moment or diffusion schemes. Yeah, and of course, if you get very extreme configurations like the emission coming only from a relatively flat disk, say, this might happen in the collapsar scenario where you form a black hole and you have an accretion disk around them, then moment equations, moment approaches will become more inaccurate. Yeah, you can find a regime where those break, but they are reasonably good approximations. These days, they have some downsides when it comes to reconstructing the exact distribution of neutrinos in angle. That matters for certain problems when it comes to flavor conversion. But in the comparison so far, they fare quite well. Yeah, then there was a question, how can you decide which K to use? Yeah, as the answer is probably similar. So you would take these flux limiters, apply them in a 1D supernova simulation compared to a Boltzmann solution, or you can also apply certain physical constraints. So for example, you can ask, do these various flux limiters comply with the principle that the distribution function for neutrinos can never become bigger than 1 and things like that. Yeah.
Any other question?
Yes. Any more questions?
I think we can end this part of the lecture and then hand it over to Aditya.
Yes, good. Yeah. So have fun with these transport problems with the Python code.